Today, we want to continue convincing ourselves that Calc 3 is easiest of part of calculus because we already know so much. We've already worked out this derivative business, which means we worked out this limit business, and we've already worked out this integral business. So we know what these things represent. Here's an application of derivatives. I want you to find the equation of a line, tangent of the function f of x at x equals 1. So I'm asking you to find the equation of a line. That means we need to have a point and a slope. So we need two pieces of information. We need a point and a slope. I've given you half of a point. I want the equation of the line tangent to f of x at x equals 1. So for our point, we'll just plug 1 into the function. And so our point is 1, 3. Next part. It's the equation of a line tangent to f of x at x equals 1. Tangent lines mean we need derivative, and that's where we're going to get the slope. So tangent will be the derivative evaluated at the point we're interested in. So the slope would just be f prime at 1. So we need f prime. F prime of x is minus 2x. And so when we plug in 1, we get a slope of negative 2. At this point, we've written down way too much just because I'm trying to explain the process. Trying to remind, not really explain, trying to remind you of the process for this. But none of this is stuff that we would need to write down. That's why I picked such a simple function. So from here, we can write down the equation of the line that we want. Y is equal to 3 when x is equal to 1, and y decreases by 2 whenever x increases by 1. You may have done a little bit more work and written the equation in the form y equals mx plus b. I don't know why. We're not interested in what's going on when x is 0. We're interested in what's going on when x is 1. Center the equation at 1. Feature the 1. Don't just always snap back to 0. Also, no calculation required except for some multiplication and some addition. Any questions? You're like, of course not, Leach. This is a problem from Calc 1. We're experts in Calc 1. First of all, no, you're not. And second of all, yeah, true. Of course not. The big question is, what am I going to do now? How do I change this problem to fit Calc 3? What changes? What am I going to do? Was that another variable? I'm not just going to have f of x. I'm going to have f of x and y. So good call. That's one of the things that we're doing around here. We're just taking, and instead of just f of x, where it's all boring, and we got these one-dimensional curves, I'm going to throw in another variable, f of x, y. Cool. Now, you don't know what equation or what function I'm going to be writing, but you know it's going to be a function of two variables. That's one of the changes. What's the other change that I'm going to be making? What's the other thing that has to happen? Got this first one covered. You don't know what the function is, but that's okay. Y'all aren't allowed to read my mind. How's this second sentence going to change? I see two things that are going to have to change.
A plane.
Equation of the plane. Instead of saying equation of a line, I'm going to say equation of the plane. Tangent to f of x, y. That's a trivial change. We've already made that one. What else has to change? Yeah. Yeah, exactly. The other thing that's going to have to change, I said tangent f of x at x equals 1. That's going to have to change as well. Because if I have a function of two variables saying at x equals 1, you're just sitting there waiting for the next piece to show up. So I'm going to have a function of two variables. I want to say find the equation of the plane tangent to f of x, y. That's a trivial change at 1 comma. And then I have to have another point. Any questions? Oh, let's write this down. I don't have a lot of imagination, so I'm just going to go 4 minus x squared minus y squared. So I need some other points. So let's go 1 comma, let's see, 2 or 3. Let's make a negative as well. So 1 comma negative 2. That's how we upgrade. We're just adding one dimension to the stuff. Instead of a curve in R2, R2, I need a surface in R3. Question, though, has the same format. Find the equation of a plane. This is what we're looking for. We want to find the equation of a plane. And for that, we need a point. And not just a slope, not just dz dx. I'm also going to need a dz dy. So I need a point and two slopes. Finding a linear equation, all we need is a place to start and a direction to go. In this case, two directions. Point, easy enough to deal with. I'm just going to find f of 1, negative 2. So our point is going to be 1, negative 2, negative 1. I just take the point I'm interested in and find out what the other coordinate is. So our point, 1, negative 2, negative 1. So we're going to be seeing an x minus 1, y plus 2, and z plus 1. And here we have finally run into something new. I've got a function of two variables. I'm trying to find the equation of a tangent, in this case, a tangent plane. That means I need two slopes. I need a dz dx and a dz dy. Those are the two slopes that I need. Need two derivatives for dz dx and dz dy. Oh, I thought 4. That's a weird connection. I need two derivatives, where in the previous problem, we were being a little bit Newtonian. We're like, oh, f prime of 1. but we needed dy dx. How is y changing with respect to x? Here I need to know two things. At this point, how is z changing with respect to x, and how is z changing with respect to y? So task number 2 for today. Where are these derivatives going to come from? How are we going to get these derivatives? We know we can't just write f prime. Prime says take the derivative of the function. That was when there was one variable, but now we've got 2 variables. Don't worry about the notation though. Find me 2 derivatives into which we can plug this point so that we can find the 2 slopes that we need in the equation of this point. A minute to think about it. Put the camera up, it makes it look like a robot with arms. Right now it's waving. Michael Jackson. What do we want? What do you think we're going to write for dz dx, the derivative of z with respect to x? This is terminology we haven't even used yet, but we know what it's aiming at. We know it's aiming at a slope. How is z changing with respect to x? What could we write for this? What's the derivative of 4 with respect to x? 0. What's the derivative of minus x squared with respect to x? Minus 2x. I bet that's part of it. How is minus y squared changing with respect to x? That's the question that we've run into. How is minus y squared going to change what happens to z when x is changing? We're looking at what happens when x is changing. How is this minus y squared going to affect anything? If by your silence you mean it isn't, that is correct. We're looking for the change in z with respect to x. This minus y squared doesn't have any x in it. Doesn't care what's going so z doesn't care what's going on with respect to x at a particular y value. It's only concerned with the x. So we think of the minus y squared as being constant in the derivative with respect to x. The minus y squared term we're going to treat as constant in the derivative with respect to x. We're looking at what happens when x is changing. I don't care about any y values. So our derivative with respect to x is just minus 2x. Now I need for a slope, I need the derivative at a particular point. So I need dz dx evaluated at the point 1, -2. And here we have the Leibniz notation. So I'll do this one. So z, at this point, z decreases by 2 when it is 1x increases by 1. That's our slope in the x direction. We need another derivative. And the thinking is going to go the same. 4 is constant. Now we're taking a derivative of z with respect to y. How does z change with respect to y? 4, that doesn't matter. Derivative of constant is 0. What are we going? How are we going to look at this minus x squared when we're taking the derivative with respect to y? We're going to imagine the minus x squared as being constant. So the derivative of the minus x squared is 0. And so our derivative with respect to y is just going to be minus 2y. So our derivative of z with respect to y evaluated at 1, -2 will be -2 times -2 this time, or double -4. The minus x squared term is constant in the derivative with respect to y. We're only concerned about the change in an x direction and a change in the y direction. Now you might be thinking, dude, there are more directions than just x and y, but every direction in the plane is some combination of an x direction and a y direction, because I and j span that plane. So once we get x figured out and y figured out, we can figure out any other direction. I didn't tell you how to do that yet. That's for later. And when we get there, you can probably guess I'm not going to tell you how it works. I'm just going to say, I wonder what this is, and then walk out the room, as is my usual plan. The strategy is make y'all do the work. I don't have to. This is why teachers retire, because they just solve that, make them do the work problem. And when teacher work reaches 0, you wait for a few years, someone notices, hey, Leach, you haven't done anything for a couple of years. Like, oh, here are my retirement papers. And then you sneak out before anybody notices. Now, if we can only figure out how to, pay people. But now I've got the pieces that I need. I've got a point, I got an x naught, y naught, and z naught. And I've got a change with respect to in z with respect to x, and a change in z with respect to y. I'm going to put it together in the same way that I always put together my linear functions. Z equals z naught, so it starts off at -1 and changes by -2. When x increases by 1, so it's going to be x minus 1. I'm going to run out of space. I even thought to myself, dude, you're going to run out of space. And I was like, oh, it'll be fine. So let's build our equation. So z starts off at -1. Of course, z starts off at -1. And the dz dx is -2 times x minus x naught. And x naught is 1. dz dy is 4. Times y minus y naught. And in this case, y naught is negative 2. Questions? I constructed this equation in a plane the same way I constructed the equation in a line. If I had a function of 3 variables, here's gone one more term. Minus dz dw times w minus w naught. Everything else would have looked the same. I would have, if it was a function of 3 variables, I would have needed a point and 3 slopes. And we would have found them the same way. Any questions? Told you, Calc 3 is the easiest part of calculus. I get to make that claim because I consider building a library of functions like from chapter 12 to be kind of a semester-long project. And we move on to more various things without having chapter 12 fully in place. Because chapter 12 doesn't fully come online in your mind until well after you've graduated and thought about surfaces more. That makes sense? The math class that you're in is never really done until years later. That's just how this works. You don't understand arithmetic until you start getting through algebra. You don't understand algebra until you start dealing with calculus. You don't understand calculus until you actually get a degree in math. Then you realize how much you don't know. Make sense? So when you're taking a derivative, that's the only one that matters. All the others are constants. I'm taking derivatives of functions of more than one variable. It's the only one with respect to is the only one that matters. The rest are constants. Now there's a variation on this theme. In this problem, I had the x squared and the y squared as separate terms. Y squared was a constant term with respect to x. X squared was a constant term with respect to y. That's constant terms included by addition and subtraction. There's other ways we can include constants with multiplication. So let's let f of xy equal 2 x cubed y to the 5th. At the same time, I'm going to introduce the variation on prime notation. We've got our Leibniz notation. I can have df dx and df dz. Sorry, df dx and df dy. But I want to have the variation of prime notation. So instead of saying f prime, because that didn't make any sense, I got 2 derivatives. I can't just say prime. We do this. Fx of x, y. That's the derivative of f with respect to x. That is the derivative of f thinking that y is constant. And the other one. So fx at xy fx at xy, we use a subscript instead of a prime because we have to say what variable is being respected. And then fy at xy is the derivative of f with respect to y, that is, x is constant. The difference with this function is that now our constants aren't terms, our constants are included with multiplication. So take a moment and find these two derivatives, even though I haven't told you how to find partial derivatives. What's the only x factor going around here in this function? The only x part of this is x cubed. 2 is constant because 2. This is a derivative with respect to x. So y to the 5th, that's constant. That's a constant multiple. So we just carry that along and take the derivative of x cubed. So 2 is constant factor. Y to the 5th is constant factor. The derivative of x cubed is 3x squared. And y to the 5th is constant. X is the variable here. Y to the 5th is constant. Then, of course, we don't leave it this way. We get 6x squared y to the 5th. We had 6x squared y to the 5th. Everybody's like, oh, I do. I mean, I did. I do now. In this case, the y to the 5th gets carried along because it's a constant factor. It's like saying 2x cubed times another 5. It's a constant factor, carries along. In the previous example, the y part was a constant term. The derivative of a constant term is 0. So fy, the partial derivative of f with respect to y, 2 is constant. X cubed is also constant with respect to y. I only care about the y stuff, and the derivative of y to the 5th is 5y to the 4th. We wouldn't leave it all broken down this way. 2 times 5 is 10. X cubed y to the 4th. The only other thing that we need to note here is that we have derivative with respect to x and the derivative with respect to y. We call these partial derivatives. Well, it's all multiplied together, and we write our constant coefficients first. So we call these partial derivatives. Say the partial derivative of f with respect to x and the partial derivative of f with respect to y. The other thing that we should note is that instead of writing dz or df, well, dz dx, we use a weird looking d. we want to indicate that we are taking partial derivatives. So in this kind of notation, this Leibniz notation, we use this partial derivative style D. That's how we let our reader know that we are doing partial derivatives. You know, us mathematicians, we love some. Any questions? How's everybody okay? All we need to do now is adapt this derivative business. Instead of just being in components with this, the X direction and the Y direction, we need to figure out how to put it in any direction. What if I care about how Z is changing in the direction of, let's say, 1, -2? What if I want to know what Z is going, how Z is changing in that direction? Right now, we know how to calculate derivatives. We got product rule, quotient rule, chain rule. Partial with respect to X, Y is constant, either a constant factor or a constant term. Partial with respect to Y, X is a constant factor or constant term. All we need now is training on taking partial derivatives. Any questions? Comments? Snide remarks? Told you, Calc 3 is the easy part of calculus. We're on easy street now. Until vector calculus, but that's another story. All right, that's going to do it for today. I will see you all on tomorrow. We have just taken our first step into chapter 14. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.